This video is going to show you how to use conservation of energy with conservative forces and the work done by non-conservative forces to solve a problem. Yves Rossy has invented jet power wings that he can strap onto his back so he can fly. He's really done it. He's got YouTube videos and everything. On one flight, he is traveling at 40 meters per second. His jet engines generate 4,000 newtons of thrust for 30 meters as he climbs upward. At this point, he begins to glide to an additional height of 20 meters. During the entire 50-meter climb, he experiences work due to drag of 12,500 joules. If Yves's jet wings have a combined mass of 165 kilograms, then how fast is he traveling at the highest point? So here's Yves going up, and for 30 meters of his climb, his jet engines are exerting 4,000 newtons of force. But he coasts an additional 20 meters for a total distance of 50 meters upwards. And the whole time he's coasting up this 50 meters, he's got this work being done against him of 12,500 joules. So that's due to air resistance or drag, whatever you want to call it. So if I look at this, I know that the 4,000 and 30 meter forces, both those arrows go the same direction. So that's adding energy to what Yves originally had. And that makes sense because the force is helping him along. Now the drag, the work done by drag, that's removing energy. So when I'm going to solve this problem, I've got to pick my 2 points. I'm going to pick the lowest point because I know the velocity and the height there, and the highest point of his motion, again, because I know the question asks, what's his velocity at the highest point? So I'll sum up all the mechanical energies at the bottom, plus the work done by the jet engines, because they're adding energy to his motion since the force and displacement go the same direction. And then I'm going to remove energy, or remove work done by the drag force. So minus the work of the drag. And all that's going to equal the sum of all the energy at the maximum height. So I'm looking at my summation of the energies. I'll look at the kinetic energy plus potential energy due to gravity. And then I'll go ahead and, on my equation, add the work done by the jets and the work done by drag. And that's going to equal kinetic energy plus the potential energy due to gravity. So to figure out which of these energies I keep, I'll go through my usual questions. At the bottom of the flight, is he moving at this location? So at the bottom, is he moving? Yes, he's moving, so I'm going to keep that energy. Then I'll ask, at the bottom, is he above the other location's height? Well, no, it's the bottom. So I'm going to get rid of that energy in my equation. I'll leave the works alone, then I go for the maximum height. And so I'm going to ask, is he moving at the maximum height? And I believe he is at this case. So since that's the case, I'll keep the kinetic energy. Is he above the other location? Well, it's my maximum height. So yeah, it's above the other location. So I'll keep that as well. So this sets up, in terms of my formulas, is 1 FmV squared plus the work of the jets plus the work of drag equals mass times 1 FmV squared plus mgh. Now in the next step, when I'm putting in my numbers, you can say I got 1 FmV squared, but for the work of the jets, I have force times distance, 4,000 times 30 meters. But for the work of drag, I just have 12,500 joules. And the reason why it's just 12,500 joules is because the math has already been done. Whatever the math is, it's already been done, and that's what I'm looking for. It's just the work. So I don't need to calculate anything. I just put the number in. And then 1/2, 165 kilograms times v squared plus 165 kilograms, 9.8 meters per second squared times 50 meters. That's the total height to the maximum point. And when I solve all that, I get a velocity of 23.65 meters per second.